Greetings, everybody. Learning is a hobby here. I want to finally start in chapter 5, so we're going to do the section 5.1 summary in this video. So let's go ahead and get to it. All right, so the chapter 5, if you remember, is all about constructing the real numbers using Cauchy sequences. So first, in order to do that, we have to first develop some machinery. Namely, we need Cauchy sequences, but before we can even do that, we need some other concepts before we can even build up what we mean by a Cauchy sequence. So section 5.1 is sort of like the machinery to build up the machinery. Okay, so we'll start here with the definition. So definition 5.1.1 defines what we mean by a sequence. Let m be an integer, then we define a sequence, which we write like this: n going from m to infinity of rational numbers as any function from the set of integers where n is greater than or equal to m to the rational numbers. So it's a function from some infinite subset of the integers to the rationals. He says here, i.e. a mapping which assigns to each integer n greater than or equal to m a rational number an. And then we'll use the trackpad here. We move right on to the next definition, which is definition 5.1.3 of what he means by epsilon steadiness. Let epsilon greater than 0, then a sequence n going from 0 to infinity is said to be epsilon steady if and only if each pair aj, ak of sequence elements is epsilon close for every natural number jk. We defined that epsilon close in the last chapter, if you remember. In other words, the sequence a0, a1, a2 is ... is epsilon steady if and only if the absolute value aj minus ak less than equal epsilon for all jk. Right, so the distance between any two terms in the sequence, where their indices are bigger than the appropriate fixed natural number. If their distance is less than or equal to epsilon for any of those, then we say that the sequence is epsilon steady. He makes a remark about this because this terminology is actually not common. The above definition, he says, as well as the concept of epsilon close and eventual epsilon steadiness, which we'll define in a minute, are not standard in the literature. They will not be needed outside of this section. Of course, we need not have n start at 0. The sequence n going from m to infinity is epsilon steady if and only if aj minus ak, an absolute value less than equal epsilon for all jk greater than or equal to n. So you don't have to start at 0. It can start from any finite, value, any finite natural number. Sorry. All right, he gives an example here just to, flesh out the concept. So he gives a few examples here. The sequence 1 0 1 0, 1 0 that go on and on forever like that is a one steady sequence, but not one half steady, because if you take differences of any of the two consecutive two terms, it's not always less than a half, less than or equal to a half. Right. However, the second sequence, 0.1, 0.01, 0.001, 0.0001, et cetera, is 0.1 steady, but it's not 0.01 steady. Okay, then another example, part 3, 1 2 4 8 16 ... is not epsilon steady for any epsilon. He does ask, like he usually does in the book, why, can you prove this, or why is this true? So I'm in the habit of doing, I prove the statement. So an equals 2 to the n for the above sequence. Let epsilon be greater than 0 be chosen. Then there's an n in the natural numbers such that n is greater than epsilon by proposition 4.1. Also, 2 to the n is greater than or equal to n by my solution for exercise 435. Therefore, the distance between 2 to the n plus 1 minus 2 to the n, which, if you simplify, is equal to 2 to the n, is greater than or equal to n, is greater than epsilon. Therefore, that sequence is not epsilon steady for any positive epsilon. All right, and then finally, this example here, the constant sequence 2 2 2 2 2, et cetera, is epsilon steady for every epsilon greater than 0. Let me just turn my phone on silent so it doesn't distract. Okay, sorry about that. Okay, so just a note here, while simple, the notion of epsilon steady doesn't really capture the quote unquote limiting behavior of a sequence because it's too sensitive to initial members. So here he gives an example, like the sequence 10, comma 0, comma 0, comma 0, comma 0, and then forever on like that, just zeros forever. Is a 10 steady sequence, but it's not epsilon steady for any epsilon less than 10, even though it converges to 0 almost immediately. Right, so this concept of epsilon steady is not good enough. It's too sensitive to initial members. So we need a new concept, which we define here in 5.1.6, which he calls eventual epsilon steadiness. So let epsilon greater than 0. Sequence an, where n goes from 0 to infinity, is said to be eventually epsilon steady if and only if the sequence a capital N, a capital N plus 1, a capital N plus 2, ... is epsilon steady for some natural number, capital N. In other words, the sequence a0, a1, a2, ... is eventually epsilon steady if and only if there exists a capital N greater than or equal to 0, such that the distance between aj and ak is less than or equal to epsilon for every jk greater than or equal to n. Right, so that's what we mean by epsilon steadiness. This concept is more useful to capture sort of converging sequences that want to converge, because this concept doesn't depend on all the terms in the sequence. You can go far enough out, and then eventually you become epsilon steady for any epsilon for certain sequences. Not every not every sequence has that property, but anyway, he gives another example again just to flesh out the concept. This is example 517. 1 over n, the sequence 1 over n and going from 1 to infinity is not 0.1 steady, but is eventually 0.1 steady. For example, 1 over n and going from 10 to infinity is 0.1 steady. The sequence 10, 0, 0, 0, the one that we looked at above, is not epsilon steady for any epsilon greater than 10. However, it is eventually epsilon steady for every epsilon because it converges to 0. We haven't really talked about convergence yet because anyway, we'll get to that eventually. But anyway, here's he does ask us to prove this. So here's my proof. Let an equal the sequence. Sorry, the nth term in the sequence is defined to be 10 if n is 0, and 0 if n is greater than 0. Then the subsequence 0, where n goes from 1 to infinity, is epsilon steady for every epsilon greater than 0, since the distance between 0 and itself is always 0, which is less than or equal to every positive epsilon for all epsilon greater than 0, in other words. Therefore, an and going from 0 to infinity is eventually epsilon steady for every epsilon greater than 0. Right, so it's just some, so to get some practice with the concepts. Here's another definition that we need now, which is the definition of a Cauchy sequence. So this is definition 5.1.8. A sequence n going from 0 to infinity of rational numbers is said to be a Cauchy sequence if and only if for every rational epsilon greater than 0, the sequence n going from 0 to infinity is eventually epsilon steady. In other words, the sequence a0, a1, a2, ... is a Cauchy sequence if and only if for every epsilon greater than 0, there exists a capital N greater than or equal to 0, such that the distance between aj and ak is less than or equal to epsilon for all jk greater than or equal to n. So in other words, just so you can visualize this, what's happening is for a Cauchy sequence, all of the terms, past some indexing value, are within a sort of like an epsilon error of some number, right? Well, actually, we don't know that it's of some number because we're going to use this to define real numbers. But all the terms past some finite index lie within a distance of epsilon of each other. In other words, and that works for every epsilon. All right, here's a remark, 5.1.9. At present, we restrict epsilon to be a positive rational only because we haven't defined the reals yet. Once we do construct the real numbers, if you remember that symbol means the real numbers, allowing epsilon to be a positive real number does not change. In other words, will eventually prove that a sequence is eventually epsilon steady for every rational epsilon greater than 0, if and only if the sequence is eventually epsilon steady for every real epsilon greater than 0. He says this subtle distinction between rational epsilon and real epsilon turns out not to be very important in the long run. So really, don't worry. It's not something that you really have to worry too much about. And we'll actually end up proving that later on down the line. So here's another example, again, just to get some practice. Example 5110. He says informal here because we haven't defined the real numbers yet. So if you look at this sequence, 1.4, 1.41, 1.414, 1.4142, and et cetera, this does appear to be eventually epsilon steady for every epsilon greater than 0. Which means that it appears to be Cauchy. However, this is not rigorous for several reasons. For instance, we have not precisely defined what the sequence really is. The sequence looks, I mean, we kind of know, right? It looks like it's converging to the square root of 2, but remember, square root of 2 is not a rational number, and we haven't defined the real numbers yet. So we don't really know that the sequence is converging to something. We don't, at least not yet. So anyway. So here's proposition 5.1.11. The sequence A1, A2, A3, ... defined by AN equals 1 over n is a Cauchy sequence. So let's actually prove this. So let epsilon greater than 0 be arbitrarily chosen. I should say, I think I did this one. This is one that this is the proof that he does in the book. One of the propositions I proved in a slightly different way than he does in the book, but I think this one is the way that he does it in the book. So let me just read it out. Let epsilon be greater than 0 be an arbitrarily chosen rational number. Let n be capital N be a positive natural number, and jk greater than or equal to n. That implies that 0 is less than 1 over j, and 1 over k is also greater than 0, and they're both less than or equal to 1 over n. So that implies the distance between 1 over j minus 1 over, and 1 over k is less than or equal to 1 over n, right? Because if you subtract 1 over n from something, if you subtract a number that's less than 1 over n from a number that's less than 1 over n, you get something that's less than 1 over n in magnitude, right? Then if we want 1 over j minus 1 over k less than or equal epsilon for all jk greater than or equal to n, we just need 1 over n less than equal to epsilon, which implies 1 over epsilon needs to be, capital N needs to be greater than or equal to 1 over epsilon. We need to choose it to be a natural number, but we could do that by theorem, proposition 441. Therefore, 1 over n, and going from 1 to infinity is a Cauchy sequence. Okay, so that proves that. Next, we need another definition, 5.1.2. This is the definition of what we mean by a bounded sequence. Let m greater than or equal to 0 be rational. A finite sequence, A1 through, AN. So here, this is not an infinite sequence. It's just a finite collection of rational numbers indexed by a finite subset of the naturals. So that finite sequence is bounded by some number m, some rational number m, some positive rational number m, if and only if the absolute value ai less than equal to m for all I between 1 and n. And an infinite sequence an, and going from 1 to infinity, is bounded by m. So here, this is an infinite sequence now rather than a finite sequence. If and only if the absolute value ai less than equal m for all I greater than or equal to 1. A sequence is said to be bounded if and only if it is bounded by m for some rational m greater than or equal to 0. Right, and then we have again an example so that we can get some practice with this concept. The finite sequence 1, -2, 3, -4 is bounded by any rational number m greater than or equal to 4, right? Because the absolute value of all those things is bounded above by 4. The infinite sequence 1, -2, 3, -4, 5, -6, ... is actually an unbounded sequence. And again, Tao asks you, can you prove this? Or he asks why. So whenever I see that, I have to prove it. And again, you should do that too if you're reading the book as well. So here's my proof. Assume the sequence is bounded, then there is an m greater than 0. Sorry, should be greater than or equal to 0, but such that I won't fix it here because for some reason when I'm in Zoom, for some reason my marker doesn't write on the board. It like makes it scroll in or out for some reason. But anyway, that should be m greater than or equal to 0, such that absolute value an equals -1 to the n times n. That's equal to n, obviously, which is less than or equal to m for all natural numbers n. However, this contradicts proposition 4.4.1, therefore the sequence is unbounded. All right, and then another example here, the sequence 1, -1, 1, -1, ... is bounded by 1, but it's not Cauchy. Right, so that's a bounded sequence, but it's not eventually epsilon steady for every epsilon. Okay, here's a lemma. Finite sequences are bounded. Is this the one that I did that was, yeah, I think, yeah, so let me just make say a word here. Tao does this slightly differently than I do. It's virtually the same idea. It's not virtually, it's the same idea. I just use a different upper bound. So my proof is slightly different than his, but they're both equivalent to each other. They're giving the same thing, just do slightly different upper bounds. But anyway, let me go through it. So here's the sequence. Finite sequences are bounded. Every finite sequence A1, A2, A3, ... up to AN is bounded. So here, what this is asserting is that as long as you have a finite sequence, it doesn't matter how long it is, but as long as the length is finite, then the sequence is bounded. Okay, and we'll prove this by induction on N. So here's the base step. We'll start with n equals 1. So if you have a sequence of one that has length 1, so just there's only one member. For example, a1 is some rational number, and the absolute value a1 is also a rational number, implies that the absolute value of a1 is less than or equal to n for some natural capital N in the natural numbers by proposition 4.4.1. So that shows the base step holds, and then the inductive step. Assume every finite sequence of length n is bounded for some n and n, and consider ai, I going from 1 to n plus 1. Then the sequence ai going from 1 to n, is bounded by some capital M greater than, again, this should be greater than or equal to 0. I don't know why I forgot in both of those cases to write the greater than or equal to. But anyway, it's bounded by some rational m greater than or equal to 0 by the induction hypothesis. Then the absolute value am plus 1 either equals m is less. So I'm talking about the absolute value here of an plus 1 is either equal to m, less than m, or greater than m by trichotomy of the rationals. And in the first two cases, then I going from 1 to n plus 1 is bounded by m. In the last case, the sequence is bounded by, all the terms in the sequence are bounded by the absolute value of n plus 1. So that shows that the sequence is bounded for all sequences of natural number length. Okay, here's a note. The above lemma tells us that every finite sequence, no matter how long, is bounded, but it doesn't say anything about infinite sequences. All right, but we do want to say something about infinite sequences here in lemma 5.1.15. This asserts that Cauchy sequences are bounded. So which is exactly what it says, every Cauchy sequence an and going from 1 to infinity is bounded. However, he leaves the proof to the reader in the exercise set. So I'll do that in the next video for the exercise set. And I think that's it. That's 5.1. So it's a relatively short section. And actually, you'll see when I post the video for let me stop the screen share here for a second. When I post the video for the exercise set, the exercise set is even shorter. It's only 2 questions. Same thing for the next section. So the solution set, the video of the solutions to the exercise set is going to be kind of short as well. But anyway, we'll look at that in the next video. I'll see you guys then. Until that time, keep learning. And again, let me know what you think down below. And I'm excited to finally get through chapter 5. So, and then we can get back to Spivak. So I'll see you guys in the next video. Keep learning, guys.